Welcome to Lecture 4. We've concluded Lecture 3 by stating that the expected value of the mean square error also written as the expected value of S square equals sigma square. From this, we can conclude that the mean square error is an unbiased estimator for sigma square. We will derive these facts in the next slides. To prove that the expected value of the mean square error equals sigma square, we will not follow the proof in the textbook, but instead we will make use of lemma 2 from the WST 311 notes. This lemma requires two main components. Firstly, that we have a random vector x which follows a multivariate normal distribution of dimension p with an expected value 0 and a covariance matrix equal to the identity matrix. We also assume that we have a matrix A, which is a P by P matrix, symmetrical, idempotent, and also of rank R. Then the lemma stated that S equal to this quantity follows a chi-square distribution with R degrees of freedom. The results down here is summary results from the proof, which we will not focus on for the moment and which we might get back to later on. In order to apply lemma 2, we need to identify the idempotent matrix. The matrix over here is the matrix A, which is an idempotent matrix, meaning that A times A should be equal to A. For completeness, I will try and indicate that this matrix is actually an idempotent matrix. So it actually means that we need to take the identity matrix minus x, x transpose x, inverse x transpose, multiplied by itself is equal to the original matrix A. So that would leave us with, if we take the multiplications into the brackets, we'll find it's an indicator matrix times an indicator matrix minus x transpose x inverse x transpose times an indicator matrix minus indicator matrix x transpose x inverse x transpose plus x transpose x minus 1 x transpose x transpose x inverse x transpose. We see that that term cancel out with the inverse over here, and what we are left with over here cancel out with what we have over there. That implies then that we're only left with x transpose x inverse x transpose, which is equal to A. Since A is an idempotent matrix, we know that the rank of A will be equal to the trace of A. So, to calculate the rank of this idempotent matrix, we need to calculate the trace of the idempotent matrix. The trace of the identity matrix of dimension n is given by n, and the trace can be taken into the brackets, leaving us with calculating the trace of x, x transpose x inverse x transpose. From the properties of the trace, we know that we can swap the matrices around, which leaves us then with an x transpose inverse, which gives us the identity matrix of order k plus 1. Why k plus 1? Because x is of rank k plus 1. Therefore, we can conclude that the rank of the idempotent matrix is equal to n minus k minus 1. In order to apply lemma 2, we identified the idempotent matrix, which we've called or indicated with an A. We also need to identify a random vector, y, which follows a multivariate normal distribution. We know from the assumptions of multiple linear regression that y, the dependent variable, follows a multivariate normal distribution of dimension n with expected value x beta and covariance sigma square identity matrix dimension n. We can standardize y by subtracting the expected value to take the expected value to 0, and we can pre-multiply it with the scalar value 1 over sigma to give us a covariance structure, an identity matrix. Then, using the information or the results of lemma 2, we saw that we need to pre-multiply with the vector, which follows a standard normal multivariate, with the idempotent matrix A in the middle, and post-multiply that also with the standard normal random vector. If we take the quantity over here to be the random vector x in lemma 2, we can write this to be equal to x transpose A x, which then, according to lemma 2, follows a chi-square distribution with r degrees of freedom, r being the rank of the idempotent matrix A. Doing the algebra, we can obtain the following. Y transpose over here, multiplied with the matrix in the square brackets, times y. Then also x beta transpose, which leaves us with beta transpose x, the matrix in the square brackets times x beta minus 2 times the cross products. For the cross product, it's important to note that y transpose the matrix between the square bracket x beta is a scalar. Why? Because y transpose is actually a 1 by n matrix. The matrix between the square brackets is a n by n matrix, and x beta leaves us with an n by 1 vector, which then leaves us with a 1 by 1 scalar. Therefore, the transpose of this quantity equals beta transpose X transpose the idempotent matrix in the square brackets Y, which we then can use to get to the quantity 2 times over there. In order to get this expression over here, we need to show that this value over here equals 0, as well as this value over here equals 0. To do that, note that beta transpose X transpose times the idempotent matrix in the square brackets, if we only focus on that, equals beta transpose X transpose times the indicator matrix minus beta transpose X transpose times X transpose X inverse times X transpose. That equals beta transpose X transpose minus beta transpose X transpose, because this cancel out with the inverse over there, which is equal to 0. Therefore, this quantity here and the quantity there equals 0, leaving us with that expression over there, which is nothing else as the error sum of squares divided by sigma square. We saw above that this follows a chi-square distribution with r degrees of freedom, where r equals the rank of the idempotent matrix. We also know from the properties of a chi-square random variable with r degrees of freedom that the expected value of the chi-square random variable will be equal to r. Using this fact, we can actually show that the expected value of the error sum of squares, which is equal to this, equals sigma square times n minus k minus 1 degrees of freedom, from which we can derive that the mean square error, which we also write as S square, equal to the error sum of squares divided by n minus k minus 1, is an unbiased estimator for sigma square. Previously, we've used the least square principle to derive an estimator for beta. Next, we will use the maximum likelihood principle to derive an estimator for beta and for sigma square. The theorem 7.6a states that the maximum likelihood estimator for beta is exactly the same as the least square estimator for beta. The estimator for sigma square is equal to this expression over here. We can also write sigma hat square to be equal to the sum of square errors divided by n, which is not equal to the estimator which we derived previously. The estimator previously being equal to the error sum of squares divided by n minus k minus 2, which was also identified to be the unbiased estimator. So the maximum likelihood estimator for S squared is not an unbiased estimator. Before we consider the proof, let's remind ourselves of the likelihood function. The likelihood function of the parameter beta and sigma square given our data equals the joint distribution of the data for the parameters beta and sigma square. In our case, the joint distribution of the data is a multivariate normal distribution of dimension n with expected value x beta and covariance sigma square I n. Using this distribution as our departure, we can prove the maximum likelihood estimator. Making use of the multivariate normal distribution, the distribution of y, we can write the likelihood function for beta and sigma square as this expression. Using the fact that sigma square in, the determinant of this equals sigma squared to the power of n, we can simplify the likelihood function to this expression. In order to find the maximum likelihood estimators for beta and sigma square, we need to maximize the likelihood function. To do that, we take the log of the likelihood function. The log of the likelihood function is given by this expression. We take the partial derivative towards beta of the log likelihood, which is equal to the expression over here. Setting this equal to 0 and solving this expression gives us the optimizing point beta hat equal to x prime x inverse x prime y, which is equal to the least square principal estimator. In order to derive this estimator for sigma square, we first substitute in the log likelihood beta hat for beta. Then we take the derivative towards sigma square and then set it equal to 0 and solve will give us the expression for the maximum likelihood estimator for sigma square. This theorem supplies us with the distribution of beta hat and sigma hat square. Starting out with the fact that y follows a multivariate normal distribution with expected value x beta and covariance sigma square in, we can derive the distribution of beta hat. Using the fact that we pre-multiply y with the constant x prime x inverse x prime, we can conclude that beta hat follows a multivariate normal distribution with parameter beta for the expected value and covariance given here. The dimension is k plus 1. For the distribution of sigma hat square, please refer back to the proof of theorem 7.3f. It is important to prove that beta hat and sigma hat square are independent. To prove that, we make use of lemma 3 on page 48 of the WST 311 notes. The lemma requires that we have a random vector which is standard multivariate normally distributed. We then define S to be x prime A times X, where A is a positive definite matrix and Y equals B times X. If we then have that B times A equals 0, we can conclude that S and Y are independent. So we need to define now what is the values of A and the matrix B and see if they comply with the requirements of lemma 3. If we take B to be the constant which we pre-multiply Y with, and if we take A once again to be the idempotent matrix which we've had before, we then see that B times A equals 0, from which we then can conclude that B hat and sigma hat square are independent.